in this slide already, except intensive tillage, so plowing, turning the soil over, or even taking a hoe out to your garden and breaking up the soil with that. Anything that exposes, any mechanical means that exposes the soil to the air, and uncovers it, is tillage. And intensive tillage are things like moldboard plowing, like the big plow that gets pulled behind a tractor that actually has those blades that flip the soil over. And there are usually a whole bunch of them together, but it can be very damaging to the soil if carbon content is not watched. I think it's perfectly fine, and it's an essential part of weed control for a lot of farmers, to do tillage so they don't have to spray. They can just bury weeds. But every time you even stick a blade into the soil and introduce oxygen in there that wasn't there before, the microbes go into hyperdrive and they start just eating up all that carbon and releasing it as CO2 and other greenhouse gases to the atmosphere. So intensive tillage is something that it's for decades, it's been an enormous problem in Prt04. That's where I did a 2-year biochar field trial when I first moved here. And I really like the Prt04 area. It's just all agriculture. It was great getting to know farmers down there. But some of the stories that I heard were incredibly alarming. Like erosion so bad that it closed roads because cars couldn't get through, this much soil this deep that it washed off of fields across roads. And before I moved here, I read a paper that was published in 2002 by some real prominent New Zealand soil scientists that said that many places in Prt04 that are intensively farmed now, the topsoil there that's on the top now used to be subsoil just a few decades ago. And subsoil, in case you've never dug down that far, subsoil is like that gravelly, it looks like stuff that, after a few thousand years of erosion and natural processes, it could become soil. But it lacks the carbon and the texture qualities that good topsoil has. So in Prt04, in these places where the organic matter has declined so much and so much erosion has happened, those soils, because they can't hold the nutrients in the soil very long, they require more fertilizer because the fertilizer is not used as efficiently. More of it's lost, so more of it needs to be added so that the plants can get it. But then that gets lost, and more has to be added. And it's a vicious cycle that leads to deserts if the issues aren't addressed. And it's really not. I say this having spent the last 21 years of my life focused on nothing but soil and water and agriculture, but it's really not that. Soil conservation and just maintenance isn't that difficult of a concept. Soils need maintenance like any other thing that we use needs maintenance and care. And I'm optimistic that things can change for the better. And a big part of what drew me to New Zealand is a can-do attitude of trying new things and new approaches to solve problems. Tillage is fine as a practice. It's beneficial. It's usually done to suppress weeds. And especially if a farmer is not going to spray for weeds, it's often the best approach. And it can also be used, you can apply nutrients or manures or whatever composts, and then till that into the soil, and it mixes it all together, and that's good. But the point is that intensive tillage introduces a lot of oxygen into the soil where there wasn't a lot of oxygen before, and that makes the microbes go into overdrive, eating more carbon and then releasing that carbon as gas. So if a farmer is, or a home gardener is tilling, like turning the soil in any way, a lot, and not putting carbon back in there in some form, it results in the carbon disappearing from the soil along with the fertility of the soil. So this is just a logical consequence. Soils deficient in nutrients lead to plants and animals that are grown on those soils that are deficient in nutrients, which directly leads to malnutrition in people who are dependent on those substances, plants and animals grown on the soil. Selenium is a perfect example. If it's not in the soil and it's not added to the soil, it's not going to be in the plants, it's not going to be in the animals, and it's not going to end up in us unless we supplement. Soils are the biggest carbon sink, or one of the biggest carbon sinks in the world. Right? And what that means is for things like climate change or for nutrients, we use the terms sources and sinks. And so a source is where the substance comes from, and a sink is where it accumulates. And so when I say soils are one of the biggest carbon sinks, it means exactly that. Photosynthesis in plants pulls carbon out of the air, and half of those plants are underground and made primarily of carbon, just like all of us. And that accumulation of carbon offsets carbon emissions from burning fossil fuels and from just the consequences of modern life. There are carbon emissions going up in the air for all sorts of reasons. And one of the things that drew me to biochar in the first place was it is the easiest method for offsetting carbon emissions. Every other method I know of that buries carbon, takes carbon out of the air, carbon dioxide out of the air, buries it underground, are very expensive technological factories that, may or may not even work. I think there's one functional one that I know of in the world. But biochar achieves the same goal through using plants to pull the carbon dioxide out of the air, incorporate it into their bodies, and then rather than letting that carbon sit and slowly rot away and go up to the atmosphere, when you turn something from raw material, any kind of plant material or animal material or anything, if you take something that would rot and you char it fully, you remove it from the biological cycle of carbon and other things and put it into the geological carbon cycle. So a wood chip, if I was to take a wood chip and place it on the ground outside, it would rot away in 5 years and be gone. And maybe some trace of it would be left where it once sat. But if I took that same wood chip and turned it into biochar and put that on the soil and came back in 1,000 years, it would be virtually identical to the day I put it there. And that's something that the indigenous people of the Amazon knew. And Has anyone in the room ever heard of Prt04? Okay, so Prt04 is literally means dark earth in Portuguese, or black earth, and it is it's the soil along the banks of the Amazon River that allowed or enabled a society before Europeans arrived to flourish there, with cities with tens of thousands of people in them and roads stretching over the horizon in every different direction. The root of the source of the myth of El Dorado, the lost city of gold, is tied up with biochar and Prt04. So the first European boat to sail up the Amazon saw all these cities and just gold everywhere and roads going, further than they could see, and they saw trade and all kinds of stuff going on. And they went back to Europe, told, the King of Spain what they found, and then 100 years later, the next boat comes up, and the rainforest had just consumed the cities, and there was nothing but archaeological evidence to be discovered in like the 1960s left of these societies. And the myth, it was called a myth because scientists of the day said, oh, these rainforest soils are too poor to possibly supported a large society. And that's true. That's why slash and burn agriculture is such a problem. It's because the soil doesn't stay fertile for very long, naturally. But what the indigenous Amazonians figured out was that if they took charcoal and compost ingredients, like fish and things that they had being on the banks of the Amazon River, if they took those materials and incorporated those into their agricultural soils, they could grow their crops there year after year, decade after decade, and even now, there are farmers growing on those Prt04 soils in the Amazon with adding no extra nutrients, no additional nutrients, to this day, hundreds of years after they were last made. The newest ones were made 500 years ago, because after that first boat came up through the Amazon, smallpox or some other microbe completely decimated all of the society. And that's why when the next boat came back 100 years later, the rainforest had consumed everything, because it was like a plague came through. And so the people who survived, left those cities, and they were living as hunter-gatherers. And so then when the next boats came through, all they saw were hunter-gatherer people, and couldn't see through the dense rainforest, the ruins of the cities that had existed for 1,000 years or more. And it was just, it's just fascinating. There's a documentary called BBC documentary, I think it's called Lost City of Gold or something like that. But if you just, BBC documentary on Prt04, it's on YouTube. It's just fascinating, and I think a lot of people it's really great. So when I was at Cornell working with biochar, the professor I was working for, along with some of his colleagues, put a paper out that estimated that 17% of all human carbon emissions could be offset if all available waste materials were turned into biochar and prevented from rotting away. That 17% of anthropogenic, human-caused carbon emissions, so that's like cars, tractors, manufacturing, all of it, 17% could be offset or made up for by wide-scale production of biochar. And there's another benefit of producing biochar is the way it was produced by the Amazonians and by the Maori and by every culture on Earth at some point. Charcoal was made by digging a hole in the ground, starting a fire, and then smothering that fire with soil and to choke off the oxygen supply. And what happens is the fire continues to burn, but it burns without oxygen. And that may sound like a contradiction of terms, but burning without oxygen is called pyrolysis. And that's what's done to make charcoal. And it's how how you end up with charcoal instead of ash. Because pyrolysis is combustion in the absence of oxygen. So it leaves, like roughly 50% of the dry weight of whatever you're burning intact as charcoal, whereas if you burn something all the way down to ash, you're left with like 1% of white ash. Its soils and biochar are still in debate about whether it's going to count for carbon credits in New Zealand, and the UN is much more open to it. We made biochars from food scraps, from paper mill waste, from multiple different species of hardwoods, different species of softwoods, and a number of other materials. And also we produce the biochars at like 4 or 5 different temperatures that were 50 degrees Celsius apart from each other. And it's really, I think it's one of the coolest biochar papers out there, because it shows not just what the quality of the different biochars are, but we then grew maize in soil in a glass house with all of those biochars and measured how it affected plant growth. And I hooked up funnels to the bottoms of the pots and collected all the leachate water that came out, so that I could determine which biochars were best at holding nitrogen in the soil and reducing nitrogen leaching into groundwater. So you can make biochar from anything that will burn, but typically you only want to make it from things that would make good compost or clean wood. So this is a picture I took of my old boss, Johannes Lehman at Cornell, and this is in a field trial that I started for him in 2007. And it's a long-term field trial in New York State, just a few minutes from the Cornell campus. It's on a very large research farm that Cornell owns, and that they will own for eternity. And it was such a great opportunity to start a biochar field trial there, because I tested it and monitored it while I was working there. But since I graduated and moved on and left, every year students and researchers are going back there and monitoring this site and seeing what the effects are 10 years out, soon 15 years out. And so that's just a picture of my old boss's hand pouring some biochar onto the unamended soil. And here's another one where he pulled maize stalk out of the ground. And this is soil that had been amended with biochar already. And you can see the dark parts of the soil that are biochar mixed together with a nice clay soil. So this is just a detailed photo of the biochar that we used in that field trial. And this biochar arrived to us in metal barrels, numerous large metal barrels. And this biochar was made from corn stover. So from the leftovers after corn harvest, the cob and the stalk and the leaves and everything. We wanted to see how converting that stuff into biochar affected the soil compared to letting those same materials rot in a neighboring plot. And the results were interesting. It was beneficial. We did all kinds of application rates and methods, and it did no harm in any of the circumstances, but it did help. It did benefit in certain ones. When you think of charcoal, you probably think of like charcoal bricks or lumps for the barbecue. And that is what charcoal made from wood looks like. If it's big chunks of wood put into the kiln or the machine to make charcoal, that's what it comes out as. But if you make charcoal from corn stover, maize stover, this is what the charcoal ends up looking like, and it's a very fine powder. Once you put it in the soil, it's there forever, and that is a very good thing. You know, like imagine if you could apply a compost that was good forever. That's a lot of what this is comparable to. The benefits of compost, the benefits of biochar are they're almost the same. And when you compost biochar or add biochar to a compost feedstock and compost them together, it makes them both better. And some German colleagues of mine published exactly that, going back as far as 2010, and it's just been shown all over the place to be true ever since then. That yeah, if you mix biochar with your compost, it makes the compost better in terms of its effect on the plants in the soil, and it makes the biochar better, because when biochar is produced through combustion, there's a combustion oils and stuff that are on there. Even if you're using like maize stover or wood, like there's combustion products that form like an oily film. Like if you look at this stuff under like an electron microscope, there's a film on very fresh biochar, unless it's been treated, and the microbes eat that stuff right up in compost. So it encourages the microbes to grow in the compost by feeding them, and on a microscopic scale, charcoal biochar looks like an apartment building for microbes. It's just like if you took a piece of wood and you can do this with like wood charcoal and look at it closely, the cell walls are still there, but the insides have all been obliterated by heat. So it's just like an apartment building for microbes, and they can colonize it, and they can hide in there, and they can leave to like get food and then go back in there.